Okay. So first of all, we're going to have a very quick look at microphones, okay? So a 1-minute video just explains how they work. So let's have a look.
How do microphones work? Though they have their differences and different uses, they are all...
So we have here, let's have a look, some different types of microphones.
Condenser.
Yeah.
Nice, good job, well done. So the first one is condenser. That's the type of microphone. Dynamic, rim, carbon, piezoelectric, that's hard to pronounce, fiber optic, laser, liquid, and MEMS. Okay, thank you, well done. Good, good.
They are all transducers.
Okay, they are all what we call, let's get rid of that, transducers.
Converting sound waves to an electrical signal. The
So
dynamic
basically, what it is, sound waves travel through the air. So when we speak, sound waves are a form of vibration, okay? Now, these vibrations enter the microphone, and this is what happens.
dynamic microphone is the most common used.
So this microphone here, the dynamic microphone, is what is used mostly.
These work using electromagnetic induction.
So they work with what they call electromagnetic induction, okay? You'll learn more about this when we talk about transformers also.
Sound waves hit a thin diaphragm, which causes it to move.
So you know a normal shape of a microphone will have a top fuzzy bit here, then your sound waves will come in and hit something called a diaphragm, okay? So through the cone, like this, where the microphone is, to the diaphragm.
This diaphragm is attached to a coil surrounded by a magnet.
There you go. And then we have a coil. Yeah. And then that is surrounded by a magnet here.
This magnet creates a magnetic field around the coil. The sound waves hitting the diaphragm are moving the coil, and the coil's movement past the magnet creates an electrical current.
There we go. Quite clever. So the coil, when the diaphragm has sound waves, it will move the coil up and down. Then there's creates a magnetic field between the coil and the magnet, the way it moves like this. And then this induces or creates a current like
This electrical current is your sound signal. Loudspeakers work in reverse.
So your sound signal will be sent all the way down to your speaker here in this case. And then the speakers work opposite. So we have up, the opposite to up is down. So into the microphone, it will move the coil up, down, and the sound will travel down here. And then in here, the opposite, it will do the opposite, and then we have sound out of our speaker. We will talk about speakers more as well.
Here, the incoming sound signal moves the coil, which in turn moves the diaphragm, creating sound waves.
So I'm sure you all seen speakers when it goes poof, 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 you'll see them vibrate like this, yeah? That's airwaves.
Learn more?
Okay.
This program contains experiments which are performed by professionals. These tests are dangerous and may involve the use of hazardous materials. They should not be performed or imitated under any circumstances. All the functioning of this basic-looking box depends on the interaction.
Okay, here we have a speaker. We all know what a speaker is and what it does. Okay, it produces sound.
Between electric current, a copper coil, and a simple plastic membrane. The current and coil cause the membrane to vibrate.
So the same as the microphone, the sound wave, but it works opposite. So inside, the current will come up, coil moves, so it works. Current in, coil moves, plastic diaphragm like this, and produces the sound wave. Causes vibrations is the word.
The membrane pushes and pulls the surrounding air. Essentially, it pounds waves into the air. sound waves. By controlling the electric current that moves this small plastic lining, the speaker can make any sound imaginable. Let's look at how it works. In the enclosure are two speakers, one for low sounds and one for highs.
Okay, so you've got your low sound at the bottom, which we would normally, you could call a sub, and then a tweaker at the top. We'll look into this later.
Both have the exact same parts and work the exact same way. A permanent magnet. Diaphragm, just a plastic membrane. Stuck to the membrane, a copper coil.
So the same as the microphone, the magnet, the coil, diaphragm. The microphone, remember, sound waves travel in here, coil moves, electromagnetic field, and then current. From there into the speaker, it's the opposite. Yeah? So we make the electromagnetic field, which makes the coil move, and then we will have sound vibrations, like this.
The coil is inserted into the magnet. When the current circulates through the copper coil, it creates an electromagnetic force that pushes on the coil. By changing the direction of the electric current in the coil, we change the direction of that force. So, the coil is pushed one way when the electric current circulates in one direction, and the opposite way when the current changes direction. Since the coil is attached to the diaphragm, where one goes, the other goes too. This interaction is the key to understanding how a speaker works. All of this happens in a fraction of a second, because the current changes direction very quickly. Up to 26,000 back and forth times a second.
Okay, so we're looking at 26,000 movements per second, which is pretty fast.
How often the direction of the current changes depends on the sounds the speaker is required to make. Low notes will get the current to move back and forth about 40 times in 1 second. That means the diaphragm will vibrate 40 times in 1 second. The faster the current changes direction, the faster the diaphragm vibrates, and the higher the sound coming out of the speaker.
So basically, different types of music makes different sounds, and that causes different amounts of vibration. And that's that for now. So let's move over to our PowerPoint. Okay, so the objectives, we are going to learn about microphones and speakers, power transformers, and relay devices. Okay, so as we've looked at microphones and speakers, a microphone for short could be called a mic. Yeah, so you will see people say, pass me the mic. Yeah, it's short, or microphone. If we look at it this way, like this, that's it, mic. Okay, let's call it a mic.
Mic.
Okay, nice. This is mic. Okay, pass me the mic. Yeah.
Thank you.
Yeah, some mic is still the same. That's actually spelled mic, really, without the E. Yeah.
Yeah.
Or mic. It's just two different spellings, but it's still mic. It's a transducer, as we've learnt, converts sound into electrical signal, as we know. So the microphone, you speak in, and it sends sound as a current, electrical signal. Microphones are used such as telephones. Yeah, you'll speak into telephone. It's using a microphone. Hearing aids that help people hear if you're deaf. Motion picture production. Okay, so like movies. Recording audio engineering, radios, megaphones, which are them loud things you can speak through, radio, and television. They're all things that use mic and speakers. And obviously with our phones or our computers, there's something called speech recognition, which when you speak, the computer understands your voice and your commands. So if you said, I don't know, hey Bixby, call my mum, speech recognition, we'll call my mum. Okay, microphone. we know it's a device that converts, changes sound waves into electrical signals. And this can be stored on audio media. I mean, tapes is old now, so cassette tapes, but not so much. Gramophone, CDs, USB drives, hard drives. We can save our media, audio media, to devices now. But as we know, we speak into the microphone and through your speaker or your amplifier, however you have it set up. Okay, types of microphones. So different types. And here we have 3 different types. Okay, good. And then obviously here's the different types down here. Wireless, moving coil, yeah, and then this one here, the condenser. Okay, now to speakers. In this case, we'll call it a loudspeaker. Speakers, they come in wattage. So the lower the watt, the quieter the sound. The higher the wattage, the louder the sound, yeah? Low wattage, quiet. High wattage, loud. Boof, boof, boof. It's a device that serves to convert electrical signals back to sound waves for us to hear. Now we've learned this, okay? So in this case, we have, let's say, a video, a tape. It's coming through here through our amplifier and then straight out to our speaker. Then the vibrations, the sound waves will hit our ears. And our ears work the same way. Our ears use vibrations, the eardrum, to understand what we are listening to or speaking to, or any sounds. Right, types of speakers. This here is a closed cabinet speaker, yeah? Because it has containment around it. It's closed, yeah? It has 3 different speakers. And they all make 3 different noises. So down here, we have what we would call a subwoofer. This makes the low notes, yeah? So, boof, boof, like the drum beat, if you like, low notes. Okay, we can, mid-range, it's easy to understand because we could say it's in the middle, so mid. In the middle and then range. So this will make the low notes, this will make your mid, and then this will make treble is what we call it, a high, the sort of percussion sounds, so the tss, yeah? So they all use different types of currents and make these sounds. So we have a unit horn, and this is just a loudspeaker. It can make good noise, it can make horrible noise. Depends how good it is. Let's move on. So power transformer. These are devices that are used to convert AC signals to have an amplitude level as we need. We use transformers for many purposes. And we're going to have a look at some of these transformers now. So power transformers. Let's go like this, easier to read. Okay. Power transformer is an electrical device that converts inbound electricity. Inbound means incoming. Yeah, you can have outgoing, which comes out, inbound, which comes in. So inbound means in. So an electrical device that converts inbound electricity to a higher or lower value of voltage for specific purposes. Specific means there's different types of things it can be used for. Maybe you want to Google Translate this. It's a hard word to explain, but you will see now. When we say transformers, we're not talking about Bumblebee or them types of transformers. Yeah, Optimus Prime or whatever his name is. We're talking about electrical transformers. And we have 3 down here. schematic symbols of 3 different types of transformers. So we're going to have a look at these 3 types. Okay, who can tell me, anyone, what transformer symbol this is? Anyone?
Air
What?
air core transformer.
Nice, good job, well done. Okay, anybody?
Ferrite core transformer.
Okay, and then
Iron core transformer.
oh no, fair enough. Is that what it says in Thai? Yeah.
Yes.
Okay, I can't read that, obviously. Makes no sense to me. So here we have our air core transformer, iron core transformer, and ferrite core transformer. You'll see in this picture, air core has no lines. So we can imagine that this is just air in here. Iron core, we have a solid line. Iron is a solid material, so we can remember that like this. And then the ferrite core has dotted lines. Now in this one, it represents it as 2. So 2 dotted lines for the ferrite and 2 solid lines for the iron core. Here, 1 solid line and 1 dotted line. So you've got to be careful for this because they can be different depending on what country you're in. These are all other types of transformers, but come to that one day in the future. Your next ones will be step down, step up, and center tapped transformer, wherever that is. So let's first look at iron core transformer. So a transformer in which laminations of iron, so this is our iron core here, the gray one, and the different sections are laminations. It's what we call laminations. Let's get everybody to say laminations.
Lamination.
Lamination.
Nice, that's 6 people. Number 8, Ni.
Me. Number 8.
Is Ni sleeping again?
No.
Okay.
No, bad.
No.
เน็ตเราเก่าคุณต้องใจเย็น
Okay. Okay.
Okay, Ni. Please say lamination.
lamination
Nice, good job. So laminations are each section of this core. Okay, thank you. A transformer in which laminations of iron or other magnetic material make up parts or all of the path for magnetic lines of force that link the transformer windings. Okay, here's a quick picture of a transformer. So we come in, primary winding here, which is our coil. This is our iron core, let's say, in this example. Primary winding, copper coils. Secondary winding, copper coils. In and out. Okay, Kaujai Mai?
Understood. Razor.
Okay, good. Okay, so where are we at? Number 17 or 18? My memory is terrible. 18. Oh, 17. Okay, 17.
18ไม่ใช่เหรอ
Subject.
17 Siberian ครับผมศิรพัฒน์เปิดไม่ได้เลย
Microphone not working.
Maybe. Step me up. 18. Step me up. We're gonna step up to 18.
Okay, let's go to 18.
Okay.
มีอะไรชื่อ
Hey, buddy. Please read this. Ferrite.
Ferrite core transformer.
Nice, good job. Well done, buddy. So ferrite core are a magnetic device which uses the windings of the transformer. So I say you'll have a primary and a secondary in most cases. And then it will use the windings here and here, and other wound components. The chemical makeup of these devices help to prevent eddy currents quick rundown of eddy currents. If you have a conductive material, let's say down here, this gray thing, and then you have your AC in your coil here, and you have your magnetic field coming through your coil. Eddy currents can transfer from one conductive material and then cause an effect like these arrows here. So they can join. And sometimes, normally only in high voltage. Low voltage, you wouldn't really see eddy currents, not a lot. Okay, number, what are we at, 19?
Yeah.
Okay, buddy. Please read this.
Transformer.
Nice, good job. As it says, we have our primary winding and our secondary winding. So electricity in, electricity out. But in the middle, instead of a core or ferrite, it's just air. So too, air. So air core transformers are designed to transform radio frequency currents. So what we're looking at, yeah? Radio frequency currents. The currents used for radio transmission, they consist of 2 or more coils wound around a solid insulating substance or an insulating coil form. Iron core transformers serve analog functions in the audio frequency range. So basically designed for radio frequency. We're going to have a quick look at relays. Okay, I like relays and contactors and things like this. They're fun to wire. You've got to use brains sometimes. If you have lots of relays in, say, a panel for a line, a machine, it can become confusing. But a relay is a device that transforms, so changes electrical energy into magnetic energy to be used to magnetize the contact of the contactor so that you can change the position of the contact. By feeding electricity to the coil, you can close or open the contact, similar to an electronic switch, which we can apply to the relay to apply in control of circuits in many electronics. Now I have a video that will make this easier to understand. So let me get back to our meeting. And then tab. So let's first look at what is a relay. Let's turn it up.
Relays are one of the most simplistic components, but they're also one of the most important.
So before we start, sorry, here, this is our relay here. Okay, this function here. This is our switch side and the incoming side. Now, this, I don't know if everyone's using it, but it's called Every Circuit app. So if you have this app, you can look at this and make this yourself. Just practice. It's fun just to practice with relays. Let's watch.
The most important, because relays are the link between low-powered digital electronics and high-powered devices. Relays allow digital circuits and digital microcontrollers to switch high-powered devices on and off.
So, like he says, low-powered input, and then this can change to high-power output on certain devices.
The circuit that you can see here, this main component here, this is the relay. And a relay basically consists of a coil which builds up a magnetic field when current is passed through it. So what happens is, if I run a small amount of power through this magnetic coil, which would be inside a relay, it actually generates a small magnetic field which will actually magnetically pull a switch into the closed position to allow current to flow from the other side.
So basically, there's other components called contactors. They work in the same way. So as soon as there is current flowing through here, it will cause a magnet effect, which will pull this open circuit switch to the closed position. So the current will come through here and then magnetize and pull this currently closed circuit, opened circuit, sorry, pull the switch back to form a closed circuit.
And I'll demonstrate this now. What we actually have here are two different circuits, and the only thing between them is this relay. They're actually both electrically isolated, meaning that this side of the circuit is not electrically connected to this side of the circuit.
So easy to understand. These are two different circuits. They are physically not touching each other. There's a gap. And it's all to do with
So
magnets.
I have a DC power source here, which is running at 3 volts. And on this side of the circuit, I have an AC power supply, which could be high power. It could be the full AC mains voltage. It could be 120 or 240 volts. And it's connected to this lamp. So what happens is,
So this symbol here is a lamp or a light. Okay. Who can tell me what this symbol is? Hello. Huh?
Is it the ground?
Okay. Yeah, good job. Ground or earth. Nice.
Yeah.
Nice.
by switching on this circuit, which could be me switching on, or it could even be a digital microcontroller that switches it on based on a program or instruction that I give it. But for the sake of simplicity, I'll be turning the switch on the low-powered side, and just have a look what happens.
Okay. So he's switched it on. Let's go back a little bit. So he has now pushed on switching, and then watch what happens here. So our normally open circuit here will become
What happens?
Closed circuit.
a closed circuit, yeah? So it's caused a magnetic effect in here, which has pulled the switch shut, closed.
So you can see what's happened here. I flip the switch on the low-powered side, which is a completely separate circuit. You can see the electrons do not flow onto this side, and the switch on this side here was magnetically attracted towards the coil on the other side, because there is now a magnetic force pulling this switch towards this closed position. So it's allowed this AC circuit to run this lamp. And the lamp is flashing because it is AC and it is running in slow motion. In real life, that lamp would be flashing so fast you wouldn't be able to see it. So let's just have a closer look at that again. Focus on this portion of the screen.
Okay.
And on the low powered side, I'm going to flip the switch and watch what happens.
Bang. So he's flicked the switch, which has then closed the circuit on our relay.
The switch was magnetically attracted towards the coil, but both of these circuits maintain complete isolation. They are two separate circuits. Now, the reason why relays are so significant is because it allows digital devices, processes and computers, which run at a very low power, to control high-powered electronic devices.
So like you said here, relays are very good because it allows low power to control high-powered devices. Kajai, maybe?
Yeah, I understand.
I know, yeah, you probably understand from teacher at, but I'm just trying to teach you the English. We got one more video that we can watch and I'll explain. But with this, there is an app called Every Circuit. So if I show you this, meeting, it's not presentation, time screen. Sure. So what you have just seen there, that circuit, you can make yourself using this app. Yeah, you can download it off the Play Store, and then you can copy the circuit that you have just seen on YouTube, and you can play with it. See what you can add on your outgoing side of the relay. Have fun. Now let's go back here. One more video, okay? No. How relays work. This is a little bit more harder, but hopefully you'll understand the pictures.
Hey there guys, Paul here from engineeringmindset.com. In this video, we're going to be looking at relays to understand the main parts, the different types, as well as how they work. For all of your relay needs, check out Telecontrols, who have kindly sponsored this video. Telecontrols are one of the leading manufacturers in the automation industry.
Okay, so what is a relay? Whatever. What is a relay and why do we use them?
A relay is an electrically operated switch. Traditionally, relays use an electromagnet to mechanically operate the switch.
So we spoke about this. The electromagnet, when current goes through it, causes a magnetic effect and shuts, pulls the switch. And it's called electromagnetic effect.
However, newer versions will use electronics, such as...
And this is a solid state relay. These are newer versions, okay?
solid state relays. Relays are used where it is necessary to control a circuit using low power signal.
So here is basically what you have seen on YouTube. So we have our low current supply from our battery, runs through our relay, and then when we close the circuit this side, it goes through the current will go through the coil, cause the switch to close like that, and will allow current to run through the circuit and feed the light and the socket in this case.
Or where several circuits must be controlled by one.
And then you can have like few circuits, 1, 2, 3. Relays are very clever for controlling multiple circuits.
Signal. Relays ensure complete electrical isolation between the controlling and the controlled circuits.
So as he's explained, this circuit does not in any way touch this circuit when it is switched off in the relay. And also, yeah.
Relays are often used in circuits to reduce the current that flows through the primary control switch. A relatively low amperage switch, timer, or sensor can be used to turn a much higher capacity load on and off.
So we can use switches, timers, or sensors to control our circuits and our relays.
We'll see examples of this a little later in the video. There are two main circuits in the relay, the primary side and the secondary side.
So same as a transformer, it has a primary side and a secondary side. The primary side will contain our coil, and the secondary is our spring-loaded switch. And obviously the magnetic effect will happen between here and here, cause it to close. Well, actually it's around the whole switch.
The primary circuit provides the control signal to operate the relay. This could be controlled by a manual switch, a thermostat, or some other type of sensor. The primary circuit is generally connected to a low voltage DC supply. The secondary circuit is the circuit which contains the load which needs to be switched and controlled. When we talk about a load, we mean any device that will consume electricity.
So a load would be anything. Could be a light bulb, could be a socket, could be a fan, could be your aircon, but yeah.
Such as a fan, a pump, a compressor, or even a light bulb. On the primary side, we find an electromagnetic coil. This is the coil of wire which generates a magnetic field and current passes through it. When electricity passes through a wire, it creates an electromagnetic field.
So we know this. When we pass through our coil, let's say this is our coil, it will create a magnetic field. Okay, well, when it goes through a wire, anything, there will be a magnetic field it creates. I showed you the video, I think, of the iron filings.
We can see that by placing compasses around the wire. When we pass a current through the wire, the compasses change direction to align with the electromagnetic field. When we wrap the wire into a coil,
Here we go.
the magnetic field of each wire combines together to form a larger, stronger magnetic field.
So then when we put our coil through, our wire through our coil windings, we could say, magnetic field becomes larger, okay, and more powerful.
We can control this magnetic field by simply controlling the current. By the way, we have covered how solenoid coils work, and even how to make your own solenoid in our previous videos. Do check that out, links can be found in the video description down below. At the end of the electromagnet, we find the armature. This is a small component which is pivoted.
Okay, so we have the arm in the relay, and we call it the armature, yeah, and a pivot. So pivot means to be able to go like this, you're pivoting. So this is our pivot.
When the electromagnet energizes, it attracts the armature. When the electromagnet is de-energized, the armature returns to its original position.
As we learned before, energized means power on, de-energized means power off.
Typically, a small spring is used to achieve this. Connected to the armature is a movable contactor. When the armature is attracted to the electromagnet, it closes and completes the circuit on the secondary side. We have two types of basic relay, the normally open and the normally closed type.
Okay, so this is important. When you get a relay, always read, because they do two different jobs. Normally open would mean it would be a normally closed open circuit, so off. Normally closed would mean normally shut, okay, normally a closed circuit.
There are other types of relays, and we're going to look at these a little later in the video. With the normally open type, no electricity flows in the secondary circuit. The load is therefore off. However, when a current is passed through the primary circuit, a magnetic field is induced in the electromagnet. This magnetic field attracts the armature and pulls the movable contactor until it touches the terminals of the secondary circuit. This completes the circuit and provides electricity to the load. With the normally closed type, the secondary circuit is normally complete, and so the load is on. When the current is passed through the primary circuit, the electromagnetic field causes the armature to push away, which disconnects the contactor and breaks the circuit. This cuts the supply of electricity to the load.
Okay, now we're going to look at the newer relays, so the solid state relays.
The operation of solid state relays, or SSRs, is similar in principle, but unlike electromechanical relays, it has no moving parts. The solid state relay uses the electrical and optical properties of solid state semiconductors to perform its input and output isolation as well as switching functions. With this type of device, we find an LED light on the primary side instead of an electromagnet. The LED provides optical coupling by shining a beam of light across a gap and into the receiver of an adjacent photosensitive transistor.
See, well, it's completely different. We're using light.
We control the operation of this type of relay by simply turning the LED on and off. The phototransistor acts something like an insulator and doesn't allow current to flow unless it's exposed to light.
So our phototransistor will not work unless there is light. When there is light, it will close our circuit and allow current to run through. When it's dark, it will be an open circuit. And obviously, when we push our switch in and we give our phototransistor light energy, the circuit will close and allow current to run through our second circuit, if you like.
Inside the phototransistor, we have different layers of semiconductor materials. There are N-type and P-type, which are sandwiched together.
Okay, N-type and P-type, you will learn this also. It's used in diodes, which is a semiconductor. But in this case, we are looking at relays.
The N-type and P-type are both made from silicon, but they have each been mixed with other material to change their electrical properties. The N-type has been mixed with a material that gives it lots of extra as well as unneeded electrons. These are free to move around to other atoms. The P-type has been mixed with a different material that has fewer electrons. So this side has lots of empty space where electrons can move to. When the materials are joined together, an electrical barrier develops and prevents the electrons from flowing. However, when the LED is turned on, it will emit another particle known as a photon. The photon hits the P-type material and knocks the electrons, pushing them across the barrier and into the N-type material. The electrons of the first barrier will now be able to also make the jump, and so a current is developed. Once the LED is turned off, the photons stop knocking the electrons across the barrier, and so the current in the secondary side stops. So we can control the secondary circuit just by using a beam of light.
Okay, guys. So